Welcome. Come back with me to the year 2000. I am 10 years old. My older brother brings home a floppy disk that has a DOS game on it called Megazooks. He's downloaded it at school, and our family's Windows 95 computer can still run it, but it looks unlike any of the games that I had typically drool over in Electronics Boutique at that time. I'm intrigued by its text mode graphics, the retro music, and the PC speaker sound effects. Most importantly, though, Megazooks turns out to be more than just a game. It is a game creation system. It's an environment that allows me to build my own games, limited only by my own imagination. Not to mention the practical restrictions of two-color, 8x14 pixel tile-based graphics, and my lack of any programming experience up until that point. So Megazooks was my introduction to programming, and it occupies a pretty weird niche in that respect. In 1993, a teenager named Alexis Jansen became frustrated by the limitations of existing game creation systems and chose to build her own system named Megazooks. She also created an original programming language for it named Robotic, which is used to program the objects known as robots in Megazooks games. So this is a robotic program. There's a few aspects we'll go through here. A robotic program, it has an instruction pointer, and that pointer always starts at the first line of the program. And then each subsequent line is a separate independent command. This is really echoey. Okay, there are no functions. There's no subroutines. There's no procedures. No blocks. No scoping. It actually has a lot in common with BASIC and assembly language in this way. A robotic program's instruction pointer always moves to the next line unless it's redirected. Unlike BASIC and its line numbers, these redirections take the form of labels in the program, as you can see here. This program establishes two labels, NS walk loop and east-west walk loop. This program also has the ability to directly interact with the game environment. These lines cause the physical object to move around the game world according to the cardinal directions. And then we can create loops by using conditionals and unconditional jumps. So in this case, we have a conditional that checks whether the X position of the player is to the left of the X position of the robot. And if it is, then we jump back to the loop label and continue execution from there. Otherwise, we fall through. Like I said, there's no blocks. You always, as we can see at the end, if we want to go back and restart the original loop, then we just use an unconditional goto if the conditional fails. The other interesting thing about robotic is that you do not declare variables. There's no stack, there's no heap like you might expect from other languages. All state is either stored in an integer global variable or through directly interacting with the game environment. This is unstructured imperative programming taken to its logical extremes. So here's another program demonstrating these principles. This program stops execution almost immediately after setting up a variable in order to track some state. The touch label is one of several built-in ones that are triggered by external interactions with the game world. When the player tries to walk through this robot object, its instruction pointer will immediately be reset to the touch label and continue execution from there. And the star is Megazooks' equivalent of printing to standard out. So what happens when there are multiple robots? When do their programs actually run? This introduces the notion of concurrency into this environment. So we take two sequential programs, and we find a way of automatically interleaving their execution. So for some languages like JavaScript, these rely on what we call run-to-completion semantics. And that means that a script will continue executing until it returns control to whatever ended up invoking it. And this means that infinite loops in JavaScript then take control away from whatever else might try to execute after them. In this example from the Firefox console, we can talk about three separate scripts mostly. The first one is a console.log. Second one, infinite loop. Third one, another console.log. But the third one does not get a chance to execute because of this infinite loop. And that means we never see this message. So we can demonstrate this is not actually the model that's used by robotic. We can create a program with an infinite loop inside of it. In this case, we set a variable to the value 0, and then we have a loop that just changes the color of this robot every time and increases this color number. And since there's only 256 colors, we then reset that value to 0 once we reach 256. And so there's this infinite loop, and it has no actual way of yielding control to anything else. So we can observe that if we run a game that has two of these robots with an infinite loop, if we were using run-to-completion semantics, one of them would be changing color and the other one would not. But we'll see that this is not the case in Megazooks, and they use a different model. Here we see, yep, two robots, rapidly changing color. They both have the same infinite loop running in them. So there's something else going on here. So, what does it mean for multiple robotic programs to execute concurrently? Megazooks uses a preemptive execution model. So each robot is allowed to execute up to 40 commands. If at any point in these commands it yields control by executing a wait command, for example, then the next robot resumes execution. So given that every program is actually encouraged to modify the game environment directly, as well as modify global variables with what must be referred to as reckless abandon, this may actually seem like a horrifying execution model. If you've ever written threaded code, you may have dealt with bugs that arise from mutating shared memory in unsafe ways. So let's take a look at some C code. This is a function that keeps track of a value that is shared between all different invocations. It increases that value and then prints it out. We're taught that this code is incorrect if it is used from multiple threads simultaneously. Now, why is that the case? That's because there is this operation where we read a value and then write an updated value back to it. And that means that this is an operation that can actually be interrupted. For example, if we have a thread that starts executing, and let's say that counter is currently 5, and it reads that and increases it to 6 internally, but it hasn't written it back yet. Now let's say that this thread is then preempted, and thread 2 starts to run, and it calls the same function. It reads the value in counter as 5, it increases it to 6, and then it gets a chance to write it back as 6 to the counter value. So at this point, that's fine, except that when thread 1 then gets a chance to resume execution, it still believes that counter 1, or that it still believes that counter is still 5. So it increases it to 1 to 6, and it writes 6 back as well. Whereas intuitively, we might expect that when this is called twice, it should be increased by 2 at the end of both of those calls, but that's not the case. Except sometimes it'll be the case because the operating system can schedule threads however it wants, and this won't actually happen every single time. And it's this non-determinism in execution that makes debugging concurrency problems so challenging, because our tools to investigate them rely on reproducibility and consistency. So Megazooks' model of concurrency clearly poses the same risk of surprising interactions when mutating shared memory. However, it has an advantage compared to ordinary compiled C code. And that is that it does not have the same non-determinism problem. So Megazooks chooses a consistent, reproducible execution order for each robot, from the top left to the bottom right in sequence. That means that if the game author encounters an unexpected behavior, they can simply restart over and over to better understand it, observe it, and ultimately fix it. Now, robotic also claims to be an object-oriented language in its documentation, but from the samples we've seen, there's no instances of classes, there's no inheritance that we're used to seeing. So let's investigate what this means. So object-oriented programming originated in 1967 in research. There was a language called Simula 67, which emphasized encapsulating data and behaviors together inside something known as objects. And Simula 67 relied on classes and inheritance, familiar things like virtual methods, in order to focus on decoupling interfaces from implementation details. But for some researchers, this was not enough. And this led to the introduction of Smalltalk in 1972. And so Smalltalk focuses instead on the way of communicating between these objects. And so rather than invoking a method, Smalltalk focuses on sending messages between objects and allowing objects to determine whether they actually respond to that message or not. So instead of a single static interface, you have many dynamic different objects that can determine if they fulfill that interface contract or not. But in both branches of object-oriented programming, the goal is always to enable abstraction while maintaining encapsulation of data. So, moving beyond this, in 1973, we see the first published research on the actor model of programming. This may sound familiar if you have read about Erlang or Scala at all, and it's this offshoot of object-oriented model, but with more emphasis placed on concurrency. So if we take Smalltalk's messages, but we make the message-sending operation asynchronous, suddenly we have a model that's more flexible. We can run each actor independently. They'll receive messages at some point, and Additionally, if we actually maintain the private data, and so you can't actually share it or modify it, then you can actually run your actors anywhere in different processes and different threads on different computers, and this makes the whole model much more flexible. So it turns out that robotic is actually this weird mix of Smalltalk and Erlang, but without any of the actual data encapsulation that they rely on. So in robotic, any robot can send another robot a message, causing that robot's instruction pointer to continue execution starting at the label matching the message name. We saw a robot earlier with a touch label, so you can think of the player and the robot as two different actors that end up sending a touch message between them when the player actually touches the robot. Additionally, you can choose, the robot receiving a message can choose to actually ignore it or decide which label should actually receive it by doing these zap and restore operations to change which label is most active at any given time. So let's recap what we know about robotic. So despite being a contemporary language, a contemporary of languages like Python and Haskell and C++, it actually ignores any kind of procedural programming style and focuses entirely on unstructured go-tos. It embraces the worst parts of shared mutable state, despite ostensibly being object-oriented. Finally, it relies on a concurrency model that had been mostly ignored by the industry for 15 years before that, and yet has actually seen a resurgence about 10 years after Megazooks came out. So it's a very weird niche, like I said. But I think there's a couple reasons why the unusual choices that robotic makes end up actually being overall beneficial. One is that the actor model implicitly steers the author towards useful programming practices like separation of concerns. Like the Unix philosophy of minimalist modular software development, some universities teach compiler classes that are based on nano passes rather than a big overall monolithic compiler. And the theory is that it's easier to create and reason about multiple small programs that focus on their own responsibility than it is to create one single larger program that replaces them all. Additionally, Megazooks' consistent and deterministic model of concurrency minimizes the biggest difficulties with the subject, turning it into something that can be understood intuitively even by new programmers. Robotic does not exist in isolation, though. It's deeply intertwined with the visual Megazooks environment, which provides a tactile experience like the Logo language's Turtle object for new programmers, or Khan Academy JavaScript exercises. Georgia Tech even created a new introductory CS curriculum in 2002 based around manipulating pixels and sound waves, and they noticed that failure rates for non-CS majors improved dramatically as a result of taking that course. So robotic fascinates me because it's a snapshot of a specific problem. Alexis Jansen needed a way to make complex games. The solution is a scrappy language designed by a teenager in a short period of time, yet since its inception, it's helped create over 2,200 games by people with varying programming experience. There's a symbiotic relationship between a programming language and its tools, and the value of a language does not exist in isolation. It must be understood in the context of the tasks that it's designed for and the audience for whom it is intended. So like Alexis, I wanted to make games, and really the fact that I learned to program through this wacky language is mostly a happy coincidence, but I do have to credit robotic with teaching me about concurrency before I ever knew that I needed it.